Lecture 9.5, Testing Convergence at Endpoints. This lizard is on a piece of petrified log at Petrified Forest National Park in Arizona. And here is another view of Petrified Forest National Park. Remember the ratio test. If the summation of a sub n is a series with positive terms, and the limit as n approaches infinity of a sub n plus 1 over a sub n equals L, then the series converges if L is less than 1. The series diverges if L is greater than 1. And the series is inconclusive if L equals 1. This section in the book presents several other tests or techniques to test for convergence and discusses some specific convergent and divergent series. The nth root test. If the summation of a sub n is a series with positive terms and the limit as n approaches infinity of the nth root of a sub n equals L, then the series converges if L is less than 1. The series diverges if L is greater than 1. And the test is inconclusive if L is equal to 1. Note that the rules are the same as for the ratio test. Example, the summation from n equals 1 to infinity of n squared over 2 to the n. We have the nth root of n squared over 2 to the n, which we could rewrite as the nth root of n squared over 2. If we evaluate the limit as n goes to infinity of the nth root of n squared, that's the same as the limit as n goes to infinity of the nth root of n quantity squared. Now what happens here? Let's investigate. The limit as n goes to infinity of the nth root of n could be written as the limit as n goes to infinity of n to the 1 over n. And now if we exponentiate and take the natural log at the same time, we get e to the limit as n goes to infinity of the natural log of n to the 1 over n. We can move the exponent out front of the log, and we get e to the limit as n approaches infinity of 1 over n times ln n, or e to the limit as n goes to infinity of ln n over n. This is indeterminate, so we use L'Hopital's rule. Taking the derivative of the numerator and the denominator, we've got e to the limit as n goes to infinity of 1 over n divided by 1, which is e to the 0, over 1. So that we don't have to do this every time we need it, we memorize the formulas. The limit as n goes to infinity of the nth root of n happens to be formula number 104 on our formula sheet. And the limit as n goes to infinity of ln n over n is formula number 103. So the limit as n goes to infinity of the nth root of n squared is 1 squared, or 1. So our original limit is 1/2. Since the absolute value of 1/2 is less than 1, the series converges. Another example, the summation as n goes from 1 to infinity of 2 to the n over n squared. If we use the nth root test, we have the nth root of 2 to the n over n squared, which is 2 over the nth root of n squared. So we have the limit as n goes to infinity of 2 over the nth root of n squared, which is 2 over 1, or 2. Since the absolute value of 2 is greater than 1, this series diverges. Remember that when we first studied integrals, we used a summation of rectangles to approximate the area under a curve. This leads to the integral test. If a sub n is a positive sequence and a sub n equals f of n, where f of n is a continuous positive decreasing function, then the summation from n equals big N to infinity of a sub n and the summation from big N to infinity of f of x dx both converge or both diverge. Example, does the summation from n equals 1 to infinity of 1 over n radical n converge? We look at the integral from 1 to infinity of 1 over x radical x dx, which is the limit as b approaches infinity of the integral from 1 to b x to the negative 3/2 dx, which is the limit as b approaches infinity, negative 2x to the negative 1/2, evaluated from 1 to b, or the limit as b approaches infinity of negative 2 over radical b plus 2, or 2. Since the integral converges, the series must converge, but not necessarily to 2. The p-series test. The summation as n goes from 1 to infinity of 1 over n to the p, which equals 1 over 1 to the p plus 1 over 2 to the p plus 1 over 3 to the p, etc., converges if p is greater than 1 and diverges if p is less than or equal to 1. We could show this with the integral test. If this test seems backward after the ratio and nth root tests, remember that larger values of p would make the denominators increase faster and the terms decrease faster. The harmonic series, summation from n equals 1 to infinity of 1 over n equals 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4, diverges. This is a p-series with p equals 1. It diverges very slowly, but it diverges. Because the p-series are so easy to evaluate, we use it to compare to other series. The limit comparison test. If a sub n is greater than 0 and b sub n is greater than 0 for all n greater than or equal to big N, where big N is a positive integer, if the limit as n goes to infinity of a sub n over b sub n equals c, and c is between 0 and infinity, then both the summation of a sub n and the summation of b sub n converge or both diverge. If the limit as n goes to infinity of a sub n over b sub n equals 0, then the summation of a sub n converges if the summation of b sub n converges. If the limit as n goes to infinity of a sub n over b sub n equals infinity, then the summation of a sub n diverges if the summation of b sub n diverges. Example: 3/4 plus 5/9 plus 7/16 plus 9/25 plus equals the summation as n goes from 1 to infinity of 2n plus 1 over n plus 1 squared. When n is large, the function behaves like 2n over n squared, or 2 over n. 2 over n is greater than 1 over n. If we take the limit as n goes to infinity of a sub n over b sub n equals the limit as n goes to infinity of our original series, 2n plus 1 over n plus 1 squared, over 1 over n, we get the limit as n goes to infinity of 2n plus 1 times n over n plus 1 squared, which is the limit as n goes to infinity of 2n squared plus n over n squared plus 2n plus 1, which equals 2. We could do this in several steps with L'Hopital's rule, or we could do this just in one step by using the dominant terms, 2n squared and n squared. Since the summation of 1 over n diverges, because it is a harmonic series, the series diverges. Example: 1 over 1 plus 1 over 3 plus 1 over 7 plus 1 over 15, and so forth, equals the summation from n equals 1 to infinity of 1 over 2 to the n minus 1. When n is large, the function behaves like 1 over 2 to the n. If we take the limit as n goes to infinity of a sub n over b sub n equals the limit as n goes to infinity of 1 over 2 to the n minus 1, which was our original function, over 1 over 2 to the n, which we want to compare it to, we get the limit as n goes to infinity of 2 to the n over 2 to the n minus 1, which is 1, because of course as n goes to infinity, this minus 1 becomes insignificant. Since the summation of 1 over 2 to the n converges, because it is a harmonic series, and our limit was between 0 and infinity, the series converges. The alternating series. The signs of the terms alternate. Good news! The alternating series test. If the absolute values of the terms approach 0, then an alternating series will always converge. Example: the summation as n goes from 1 to infinity of negative 1 to the n plus 1, 1 over n, equals 1 over 1 minus 1 over 2 plus 1 over 3 minus 1 over 4 plus 1 over 5 minus 1 over 6. This series converges by the alternating series test because the absolute values of the terms approach 0. This series is convergent, but not absolutely convergent. Therefore, we say it is conditionally convergent. By the way, we should recognize this series as an alternating harmonic series, and as we learned in a previous lecture, it converges very slowly to the natural log of 2. Since each term of a convergent alternating series moves the partial sum a little closer to the limit, the alternating series estimation theorem tells us for a convergent alternating series, the truncation error is less than the first missing term and is the same sign as the last term used. This is a good tool to remember because it is easier than the Lagrange error bound. There's a flowchart in your book that might be helpful for deciding in what order to do which test. The chart is also on a handout. Mostly it just takes practice. The chart is also available for download on the site below, or you can Google Greg Kelly Calculus and find the website. To do summations on the TI-89, the series at left is entered as shown at right. The summation symbol is found by pressing F3-4. The calculator returns the partial sum 31/4. The TI-89 can also find the sum of an infinite series. The series at left is entered as shown at right, and the calculator returns 8. To graph the partial sums, we can use sequence mode. We change the mode to sequence graphing. And we press diamond y equals and enter the series as shown. For this series, we'll use the following window. We'll graph the first 20 terms. And our step is 1. So x will go from 0 to 20. And we'll guess what y will be, but in this case we're going from 0 to 10. Then we press diamond graph. And these are our partial sums. Notice that they converge. If we want to look at the results in a table, we can press diamond table. There we see the first few sums. And we could scroll down to see further sums.